Good afternoon, everyone. Thank you for tuning in to this pre-recorded tutorial. My name is Yash, and I work as an optimization research scientist with the optimization firm. In this tutorial, I will discuss how Alamo can serve your machine learning and analytics needs. I hope everyone has been staying safe and doing as well as is possible during this pandemic. I also hope that all of you have figured out by now how to navigate a virtual informs meeting. A couple of quick notes before we dive in. Although this tutorial is pre-recorded, I will be available at the chat window for any questions while the video is playing. Please feel free to write in your questions and I will keep responding to them in the chat window. The meeting organizers have also promised us 15 extra minutes at the end of the video for live Q&A via Zoom. However, in case of any technical issues, please feel free to reach out to my email on the slide with your questions. You can also reach out to our company help desk at info@minlp.com and receive answers to your questions promptly. With that, let's get started. This tutorial is broadly split into three parts. In the first part, I will talk briefly about our company, the history of Alamo, and some of its key features. Alamo has been available on a trial license for a few years now. Alamo licenses are available from our website www.minlp.com. In the second part, I will briefly describe the Alamo algorithm and mention a few of its applications already published in the literature. Finally, I will go through a couple of demos that show how you can use Alamo for your applications. I hope that at the end of this tutorial, you have all the information that you need to build accurate, robust, parsimonious, and meaningful models for your datasets. The optimization firm has been a pioneer in the area of optimization and machine learning for about 2 decades now. The optimization firm was founded in 2001 to build on fundamental theoretical research combined with efficient practical implementations. We are unique in that all of our algorithms and theoretical advances are published in the open literature. We rely on continuous innovation to push the boundaries of what the field can do to maintain our competitive advantage. Our primary commercial activity is the licensing of the software that we develop. However, we are also available for consulting projects depending on our clients' needs. For more information, you can reach out to sales@minlp.com. The primary team for the optimization firm consists of Dr. Nick Sahinidis, Dr. Yash Puranik, that's me, and Aphrodite Kishi. Nick is the founder and the CEO of the optimization firm. The primary brains behind the company, Nick has carried out fundamental research in the areas of convexification, global optimization, simulation optimization, molecular design, bioinformatics, and machine learning for over 2 decades now. Nick is an Informs Fellow, and his work has been recognized with the Informs Computing Society Prize in 2004, the Beale Orchard Hayes Prize in 2006, the Carathéodory Prize in 2015, and an award from the Hellenic Operational Research Society in 2016. Nick has authored more than 150 research publications and holds 2 patents. Nick has authored the current implementation of Alamo. I work as an optimization research scientist with the company and carry out the primary development work on Baron. I received my PhD from Carnegie Mellon University in 2016. Some of my research interests include parallelization and diagnosis of infeasibilities. Aphrodite is the director of operations at the company and manages all of the company's day-to-day operations, sales, and licensing. Aphrodite works at superhuman efficiency to ensure that all sales and licensing queries are resolved within one business day. In addition, we have several developers working around the world to advance the Baron and the Alamo project. The two products offered by the optimization firm are Baron and Alamo. Baron stands for the Branch Introduce Optimization Navigator. Baron was the first optimization solver launched to solve mixed integer, nonlinear, non-convex optimization problems and provided deterministic guarantees of global optimality. Even after many competitors have entered the market, Baron remains the fastest and the most robust global solver. More information about Baron can be found from the company website. This tutorial is focused on Alamo. Alamo stands for Automated Learning of Algebraic Models. Alamo was primarily designed to build algebraic models from data with high accuracy while keeping the models as simple as possible. I will walk through a brief history of Alamo next. The Alamo project was conceived as a part of the Department of Energy's Carbon Capture Simulation Initiative. The first version of Alamo was distributed amongst the Industrial Advisory Board members of the initiative in 2013. Alamo offers a unique constraint regression capability that differentiates it from its competitors in the market. As a user, you can specify a meaningful constraint that you require your machine learning models to satisfy, such as non-negativity of variables denoting physical measurements. Alamo ensures that the algebraic model built from data satisfies this constraint on the entire domain of your application. This capability was first implemented in 2014. By 2016, Alamo was extended to build classification models. In 2017, we added the feature of group constraints. These are combinatorial constraints between groups of basis functions that make up the model. Alamo has been available for a free 3-month trial for a few years now. Historically, Alamo depended on the commercial MATLAB and GAMS software for its application. We have recently eliminated the MATLAB dependency and are now working on eliminating Alamo's dependency on GAMS. Once this work is completed, you will be able to use Alamo without having to purchase or install any third-party software. At its core, Alamo is used to build models from data. You might ask, what is so special about Alamo? There are already hundreds, if not thousands of algorithms and software products that do so in several different ways. What truly distinguishes Alamo is that it was designed to provide interpretable models and utilize as many insights to the system under study as are available. Of course, everyone would like their models to be highly accurate. A model that cannot predict the desired response variable is practically useless. However, many scientists and engineers also like their models to be simple. Additionally, in many situations, the data required to build models may be expensive or difficult to obtain. In such situations, we prefer that our models be generated from as little data as possible. Finally, in many cases, model builders can provide real insights into the system under study. Using these insights, Alamo is capable of finding better, simpler models without requiring large datasets. Although high accuracy is a necessary feature in almost all applications, simplicity is equally important for many practical use cases. Highly complex machine learning architectures, such as deep networks, radial basis functions, or kriging, have shown tremendous success in building high accuracy models for many different types of applications. However, These models are difficult to inspect and analyze. A simpler algebraic model is much easier to inspect, audit, and maintain. This is especially important in applications where safety is important and the costs of mistakes are exorbitantly high. For instance, a mistake in a recommendation by your favorite shopping website may lead to lost revenue. However, an error in a control application can lead to equipment failure or worse, loss of life. Emphasis on finding simple models is one of the primary differentiating factors for Alamo. At the same time, we do not compromise on accuracy. Our preferred region balances the objectives of the accuracy of the model and its interpretability. Thus, instead of the detailed mathematical maze of a complex model, we are interested in the elegance of a simple model, which is more likely to be closer to a fundamental truth. In the era of big data, the amount of data points available for machine learning has exploded for many applications. However, this is not true in all situations. In many cases, the data is generated through simulation models that can take minutes or hours to converge. In other cases, data is generated through laboratory experiments or clinical trials on human subjects. Simulations or experiments can be expensive and time consuming. It may not even be possible to conduct experiments for all domains for all variables of interest. Deep network architectures typically require large amounts of data and cannot be applied for such applications. In contrast, Alamo actively attempts to minimize the amount of data it needs to generate an accurate model, making it a highly desirable choice for such use cases. Often, domain expertise and practical insights are available that can strengthen the machine learning model. In other cases, obvious constraints exist on the model. For instance, a model predicting percentage of infected individuals in a population should only predict values between 0 and 100. Alamo uses such information provided by the user in the model building process to ensure that the models returned satisfy constraints specified by the users. This truly unique feature in Alamo, termed constraint regression, ensures that the models are meaningful and practically applicable. This incorporates the best of both worlds, domain expertise and data-driven machine learning. The Alamo algorithm factors in these considerations to deliver a method capable of generating accurate, parsimonious, algebraic models that can incorporate arbitrary constraints on response variables. Briefly, the algorithm proceeds by generating an initial model with all currently available data points, termed model I in this figure. If we do not have access to a simulator or experiments to generate more data points, we are done. However, if it is possible to query the system and generate more data points, Alamo will utilize its smart adaptive sampling technique. Adaptive sampling recommends optimal sampling points where maximum new information will be discovered to update Model I. This is done using derivative-free optimization methods under the hood, which perform very well in low dimensions. Once the newly sampled points are made available to Alamo, a new model is built using mixed integer programming technologies. For this step, we leverage the optimization firm's expertise in global optimization that is available through the solver Baron. Under Alamo's hood, these problems are solved with Baron. The truly differentiating factor for Alamo is its ability to apply arbitrary constraints to the response variables to ensure that the algebraic model returned is practically applicable and meaningful. These constraints can be of various forms. For example, non-negativity, convexity, boundedness, or user-defined functions. While it might seem improbable, there is no magic here. This relies on semi-infinite optimization problems. I won't go into the details of this method, but interested members of the audience can find all the details published in literature in the reference on the slide. How does Alamo compare against the innumerable competing methods available in the literature and commercially? On this slide, I'm presenting results published in Kozad et al. This figure compares the complexity of Alamo models versus Lasso models. On average, Lasso models are more complicated than the real known function used as black boxes for generating data. On the other hand, Alamo models are often simpler than the true functions while still maintaining a higher accuracy than the Lasso models. This shows the strength of the Alamo algorithm. Of course, there are no free lunches. These benefits come at the cost of more computational time to obtain the models. Alamo has been made available for evaluation through trial licenses for a few years now. These licenses have been downloaded by users across Europe, Asia, the Americas, and Australia. We've had more than 100 academics and 30 commercial entities test Alamo and provide valuable feedback that has helped create a robust product. Alamo has already found applications in literature. Alamo has been used for building surrogate models for gasifiers, for learning correlations, for fin-tube bundle heat exchangers, and for learning steam properties. Alamo has also been used in optimal production of syngas and for the production of hydrogen and methanol. The Alamo algorithm has been implemented by the company PSC in their popular simulation software called gProms. However, their implementation does not possess constraint regression capabilities. Next, I will go through a brief demo to highlight how you can apply Alamo for your practical applications. Welcome to this demo for Alamo Pi. In this demo, we will apply Alamo to a publicly available dataset from the UC Irvine repository. Alamo comes with a command line interface and a graphical user interface that can be used for building algebraic models from datasets. However, many users would like to hook up Alamo to existing application code. You can use the Python interface to Alamo called Alamo Pi for such applications. Alamo Pi is available from our company website at www.minlp.com. We will use Alamo Pi for this example and also present a brief comparison between Alamo and Lasso. Let's go through the Jupyter notebook. Our data includes efficiency of cars measured in terms of miles per gallon as the output variable of interest. Input variables considered include both continuous variables such as displacement, horsepower, weight of the car, and so on, and discrete variables including the year in which the model was launched and the number of cylinders in the engine. In Cell 2, we download the data directly from the UC Irvine repository website. Manual inspection of the data indicates that we have missing values for some rows, which are indicated by a question mark in the dataset. To keep the example simple, we eliminate rows with missing values in cell 3. In practical applications, such missing values can be estimated via suitable imputation methods. As all of you must be aware, the majority of the efforts are spent by practitioners of data science and analytics in visualizing the data, in pre-processing, and in cleanup. In this simple example, I'm just choosing to plot the efficiency in miles per gallon versus the weight of the car. This confirms what what one would logically expect, that as the weight of the car increases, the efficiency of the car decreases. So this gives us some confidence that there are no major issues in the data that is collected. We use a simple scaling step to pre-process data and remove outliers by removing points that have a z-score of more than 2. First, we apply the lasso algorithm on this dataset. Lasso is a highly popular algorithm for building models from data that are regularized. Regularized models are sparser than those returned by ordinary regression. We will be using the highly efficient implementation of Lasso from GLMNet for this example. First, we create a number of training features from the raw data and add them to the set of inputs. These include the square terms, cube terms, and so on. The total number of features used for the Lasso model are 154. Next, we randomly split the data into a test set and a training set. This will help us assess the performance of Alamo and Lasso on a test set that neither algorithms have seen before. We run Lasso with cross-validation to automatically pick the optimal choice for lambda, the regularization parameter. The Lasso algorithm is highly efficient and solves for the optimal lambda in a matter of a couple of seconds. The number of features picked in this Lasso model are 15, while the mean absolute error for the Lasso model on the unseen test data is 1.5. For the application of Alamo, we split the data into the same training and test set that was used for the application of the Lasso algorithm. This is achieved by utilizing the same random state that was used during the splitting of the data for the Lasso algorithm. We apply Alamo on this model by calling the AlamoPy.alamo function with suitable arguments. Information for each of these arguments can be found from the AlamoPy documentation on the website. Note that by suitably specifying inputs, all appropriate features are generated by Alamo automatically. These did not have to be pre-calculated and entered by the user, as in the case of the Lasso algorithm. Alamo prints out a helpful message saying that it will calculate the bounds for each of the variables from the data itself, since they are not provided by the user. AlamoPy offers a nice functionality where the model learned by Alamo is returned in the form of a Python file called cout. This can be imported and used directly in the Python code. Here, I'm reloading the file cout by calling importlib.reload and calculating the performance of Alamo on the test set. The predictions from Lasso and Alamo are compared here using a parity plot. Both the Alamo and Lasso models do a very good job of predicting the true values for miles per gallon for each car on the test set. The performance of the Alamo and Lasso model is fairly similar. However, where Alamo shines through is in the fact that the Alamo model only utilizes 3 terms as compared with the Lasso model, which utilizes 15 terms. Since the model is simpler, it can be analyzed for interpretability. Inspecting the model, we can draw certain inferences that look reasonable. For instance, the model includes a term that is the year the car was manufactured cubed. This seems reasonable since we can expect newer cars to be more efficient. This model also has a positive coefficient for the term year over weight. This is also logical since we can expect the efficiency of a car to go up as its total weight goes down, something we saw in the images shown previously. Alamo makes analytics and machine learning transparent and maintainable by providing sparse models that are more easily interpreted. I hope all of you will find Alamo useful in your work. I hope all of you can already think of the various problems you are solving where Alamo can prove to be a vital tool. Alamo is available to everyone for a trial period of 3 months. You can go to www.minlp.com, register yourself as a user, and request a trial license which will be automatically emailed to you within a few minutes. All Alamo licenses come with full access to the software with no restrictions on problem sizes. The license also allows you to run Alamo on any hardware configuration, operating system, or even a cluster. All licenses come with maintenance and support included. Alamo is currently and will always remain free for use for teaching and research for academics. Alamo licenses for academics are valid for a period of 12 months and can be renewed indefinite number of times. Alamo licenses are also freely available to all companies that are part of the Center for Advanced Process Decision Making and members of the Department of Energy in gratitude for their support in developing the Alamo product. Again, the place to download Alamo is www.minlp.com. Thank you all for your kind attention. For regular updates, please follow us on LinkedIn, Twitter, and YouTube. I will be available after this video in the Zoom meeting to answer any questions that you may have. I hope all of you have a good and productive annual meeting. Please stay safe and well.